That's ferocious whole. Like literally, I just gotta do the speech notes. Basically, I got this thing of to start recording. I didn't want to show you this kind of screen. This kind of things I want to also offshore supply things I'm actually actively processing. It should be basically I'm trying to have the scripture work as intended. Basically, she opened my mic now. Like you can see me, but I can't even access X clip no more. Recording the video, literally it works as intended. Okay. Oh, I can't even be far from the fire. Okay. What am I doing now? Tomographic integrity. Today's date is 27th of December 2025. Time now is 5:45. OBNX is Namdi, researcher and founder of OBNX, design and construction framework. Definition. Basically, Namdi, you are still here. If you're sure, don't worry about that. We're gonna go to for half row, boil, growth factor. Basically, something I was gonna do. State here. I'm going to get looked at my Uber account. I'm happy. But I got my food there and I can't even go to my food like I said. I should have brought my food here. I am a scalar. Basically, a scalar, basically, you can have you can vector as only as basically trying to reduce the dimensional principles, dimensions principles, dimensional personality framework. So literally, Heisenberg or Heisenberg principle. What am I actually modeling? What should we state of things? Chronicality. Heisenberg's associated people state that if I have one state, I wouldn't know the other state. But you know, if it's half fake, it's half true. But you know, that's kind of from as Heisenberg's associative principle. No copying, genetic copying. Basically, it's biodiversity of a genetic basically, I'm Russian basically. Directed symbiotic evolution on github.com/OBI Nexus. Direction Revolution, we don't have genetically modifying organism as a policy in the cultural framework ever again. But we're trying to let's just have chemical state for everything for mosaic systems, things that evolve dynamically. You know, especially things that grow. How should they grow? That's the problem as well addressed with Heisenberg or several people. Because if you're a center of a state, what would that mean? Because you know, as the system evolves, it has to be certain it's evolving the correct way. For its people, for anyone that is in it. It's kind of do I need something? If I don't need something, I remove it. But did I need to remove that thing? If I give it to the right people who will use it. Basically, it doesn't matter how advanced technology is. If it doesn't sustain right people, it's still a danger to the right people, the people that build it. That's the problem, really. Genetically, it's the same thing as e to the power of I pi, where I is the signal to process over the dimension 3 squared xyz. But dimensional personality framework is like based on the localized dimension of the maximum localization of interest. The space we have governed, and it should govern. With this philosophy, what do I mean? Battleship analogy. So you have a battleship. It pings. The ping is hostile, but you don't know it's hostile. So we just radio ping. So you talk to it. You start communicating with that ship, or vice versa. You start you start offering resources to that ship. It doesn't matter because it's then they start getting more resources, and then they destroy your own battlefield ship. It doesn't matter how far you go under. It's basically if you're sending the wrong information, the right information, the wrong information, the wrong people, you just hear ping. And the ping, ping, ping. It's basically the problem of dimensions. You know, am I it doesn't matter what channel you go to. It's a big issue things for battleships, literally on the ground, because you know you think you're being intercepted, but you're being just like that information, and you know the person just collects the information and collects your life the ticket obviously. A scalar definition, basically you got a vector which is a scalar as a scalar, but a vector is a scalar just has to scale the dimension of it. For example, a 2x2 vector matrix A B C D determinant times some kind of scalar x y. Say x is 10. 10, 2, 5, 2, 6, 5. Okay, this is just a number of numbers, but the matrix is 1. 1 and 1, which is our scale is 1, 1, but to the power of a half. Basically, you have this is what I define as a scalar matrix. But it is a scalar. It's a matrix, but it's like one gives. Just look at the matrix 1 1 because 1 1 is just the characteristic of them. So if this so you get to the power of 2. Basically, this is the dimension to the power of 2, but you get the one x-axis, which is just the standard scalar for growth. But you know, you have to scale it by 2, no matter the state. For example, you go to, if you have the number, if you go to, so you apply e to the power of I, e to pi is just e to the power of pi. Pi basically I measure by I is -1. So 1 minus 1 is squared. Minus 1 cubed. Basically 1 cube I cubed is what -1. -1. But this is just the axis of ijk. Basically -1 is not the ijk, so I times I is -1. But then I times the power of negative I is what 1. And I to the power 1 to the power of -1. So you get the opposite you have to adjust for. Basically, it's like you flip it. I to the power, basically, it matters because you flip the symbol, so basically you reflect the information. So basically, all you gotta do now is verify it. So I to the power of I to the power of I, negative I, is -1. So get a -1 xy equal, which is the flip of it. It's the same information, but on the polar, on the opposite axis, the full scalar, opposite scalar. So you can use the what? -1 and -1 matrix, and literally just use the same matrix to get the conjugate result. Basically, it works in dimensions. It does operation. That's what it matters to me. It's like so now if I do 10, if I perform the scale operation 10 times row alignment, so get 10 times -1. So get AD. So if this is determinant AD, let's calculate this. The method, what's the Jordan method? Is the polynomial function. So if you get the polynomial and negative b, negative b, the negative b positive was negative. A negative boy couldn't decide where to go radical party. Basically, that's square root. The party wasn't all over onto two. The party wasn't all over onto four onto. I'm thinking what's the thing? Let me think. A negative boy couldn't decide whether to go to radical party. Positively, NB this is just quadratic formula. Y equals the position of y equals negative b. A negative boy couldn't decide whether to go to polynomial form. B square. He said the negative boy couldn't decide plus or minus whether to go to radical party. That's the square the third symbol. Rational is like a square root. Radical party. That's all of let me just say this quadratic formula actually. Let me just say the quadratic formula. Quadratic formula. Basically, this is it. Basically, you apply this formula literally wherever you go. Let me just get it quickly because you got an E, but it matters because it really matters. So the matrix is if you get this matrix 20, 10, 25, you can use the 1 over determinant of a matrix. So let's calculate the matrix calculator. Because you know it's all progress of life. So and when you ping something, you really executed it. That's kind of a big problem for me. No matter how you think about it, it's so the dimension of the matrix is 10 to 10 to. So basically, this is scalar. You see that it's the power. Basically, you get its power of the matrix is the dimension of the IQ to elevate the 10 to the 10 to 25. 2 dimensions of the matrix axis, and then we get the determinant, which would be basically you get details 10 times 2 a times d times b plus c, that'll be 24/6, and that'll be details you get the same one in multiplication. So you get minus 18 minus 20 minus 15, which would be the determinant of the matrix, because a1 times a1, a2 times a2. And you get the same thing as a21, but you get the 10 times 5 minus 20. You know, you get the conjugate inverse. You get the conjugate plus, but you can work on the plus if you have the right transpose to the measures. But you know, if you have the because this 10 to can be plus, but this minus because it's termination of subtracted. I use plus because it's but I failed it because it's plus. So really, this is the right one to get. So if you do 10 times 10 times 5, 10 times 5 is what? 15. 15 plus 4 would be what? Okay. 15 plus 4 would be 15, 16, 17, 18, 19, 20. 15 plus 10 times 50. 50 plus 4 is 54. So this basically this we subtract but you know why was determinant? Why I didn't even know why I was using it, but you know I remember I was using it because I was using it because of operation I was doing. But in terms of subtract one subtract, but obviously you got some way you can offer. But I kind of signal processing. I was using the signal processing things, but you know, but you get the 1 over this kind of matrix here. So this terminal matrix. Now get the details. The row and the column. So basically you get this one -5. So you get the details of the measure rotation. So you get 5 times. You get 2 matrices. One matrix 1 A11, and then 8 times. You get I don't know where this matrix comes from. I don't even know. But this is like literally the terminal. But this is but do not see. But you can get the terminal for the matrix separately. Measurable the lower first matrix is applied to scalar matrix, which is the same thing. So you get 5 plus 8. But I don't see why the 5. I don't see where this come from. Basically, it's just giving this, I think. So basically, I want to try to get this formula down. Enter. No. Plus, basically, I'm trying to find x versus y, x. X, basically, the point of x when y changes. Basically, it's a Fourier series, literally. Plus, because you get plus, you can put minus. Let's put minus, and that'll be enter. So basically, you get minus. Basically, you get plus and minus because plus and minus. So minus AB plus minus A. Basically, I'm trying to put a number into for B, but just so you get it from x. You get the you get the following formula, which is defines x. But x is for the 6. So what would you do about this first series? The first series has 2 waves, basically. This one has 2 waves, so that's what I remember now. That's what because you get the waves opposite the waves. So the waves are Fourier series, and that's why I'm really worried because the waves are Fourier series. So this x equals in brackets minus AB minus square root of b squared dash minus 4ac squared divided by 2a. It's just what the first equivalent is because you get the minus b. For example, basically you get the inverse of it because you have to measure 2 angles of it minimum to get the right message. Because someone else might be in crisis. That might be you. But literally, it's just a stubborn one. Which a Fourier series is the same thing. A Fourier series is what a Fourier series is 2 sets of digital a Fourier series is the digital equivalent of an analog series, but 2 sets of it. But basically, you can use integration calculus to do it. But basically, go to my repository here. GitHub.com/legislation. You have used for legislation trees to calculate with them. Basically, you have 2 integration. Basically, you get 2 left directions, but one right direction, one right answer is like one polar right answer, one right equation. It's 2 equations that have opposites. Basically, you can converge the equation by 2 axes, and axes are literally just different axes like x, y, z. But for signal processing and the e to the power of how it grows and how it resolves itself in pi framework, like literally just being there. But the civil code, I don't know. I don't write with AI, but literally just the legislation or repository here. But like literally, you got basically a forensics is just the digital equivalent of an analog wave. But there are 2 answers to it. But you have to basically get 2 answers to it, and that'll be opposite based on the conjugate rules and the inverse conjugate models of the sparse structure. But literally, it's literally about this kind of operation. So when you get x equals minus b, right, minus b, you get b squared minus 4ac 2a. So 2a plus 2ab plus bc, you get the kind of the roots are where the functions start. I don't know. The roots of the equation are polar opposite, but you get a half. Basically, you get a half of the things because you scale the half. Basically, you get a half of the signal. So basically, everything. It doesn't matter how you climb. Signal is what happens in halves. Basically, everything is done half of the universe. No, it's inverse. You have to find a half of everything and nothing, which is what the eigenvalues are. You can make this an eigen matrix. For example, if you want to make this a proper signal sync and process, just take any complex number, like a complex vector. A complex vector is 2 to the plus pi, 2 to the plus I2, I minus I, 2 times 2 plus 2 minus 2 plus minus I, 2 plus minus I, minus I, plus 2 minus I2. 2i, and then that will be 3 minus 5j. Just to pay. So basically, if you take these dimensions, you can apply a rule to both of them, and that will be to the power of I, squared. So negative. Can do a half of the dimension. This will be basically of a signal. This will be equal to half of some kind. of vector. That'll be like a signal. That'll be I, but I was the imaginary unit, but I will be 1. Half of I will be so that'll be -1. So that'll be 0.5. So wherever you do symmetry, you have to apply 0.5 to it, and that'll be half. That'll be I. So this would be 0.5 is equivalent to I. I is the imaginary unit you're processing on, because it doesn't matter what the Fourier series is. You're gonna have 2 solutions to it, and that's a 2 set of quadratic equations based on this kind of polynomial system, because they use work on these polynomial. And if you make a mistake, you can always verify it in on the cost of time, because you get the full information, but you get half of the noise. Because you get half of the noise. Because you don't implode because of the noise environment. You get the information still, and you can still check how to continue. And that's the benefit. Whether you're deep sea or dive, this is why it matters. E to the power of I. So if you get I, that's equal to -1.1, but -1, and you can get -1 plus or -1. So you can do, let's do plus because let's do the operation plus or -0.5, because that'll be the same thing between 0 and 1. Because you get 3 halves, but in the imaginary conjugated one, you get the big N of 0 and 1, but you get the 3.5 one. Because the half of this is equal to 3.5 and 0, which is 0.75 is between 0.5 and 1. That's just the big numbers. That is half. That's really 0.5. The share 0.5. Wait. Half of what's half of half? 0.5. 0.5 plus 3.5. 0.5 times 3.5 times 3/4 divided by 2 will give you, divided by 2 will be 1.875, and that'll be the medium. The big N notation says that's the largest numbers in an angular vector they can compute over, but you have to divide it by 2 again, because this is just the biggest number between. So you get half plus half divided by 2, but this is the biggest number, the whole share and the medium. But this our bound is 1, so you have to divide it by 2, and this will be 0.93. Basically, you have a range of 0.25 to 0.25 to 0.025. No, 0.25. Thank you. To 0.9373. 937. This is just imagining you have a correct state. So the kind of thing you're trying to do is like literally just have all this rashes, half ratio, because you have a standard. It doesn't matter if it's a transpose matrix. You have to apply the rule that applies to that transpose rule, because that'll give you the basically, if you have a transpose matrix, what you calculate, you have the 2 transpose matrix with the same matrix, and that'll be the canonical matrix. You can work on something. If you have the same one matrix and you come with transpose, you get the row. Let me just look here. So 10, 2. 10, 2, x1, and the transpose will be 10, 2, transpose will be 10, 2, 2, 5. No, 5, 2, 10, oh wait. So basically, 10, 2, 10, 2, 5, 2, 5 equals 10, 2, 2, 5. And you get the transpose, then you calculate transpose again. Basically, you have the transpose twice, and we'll give you 10, 2, 2. Let me just do matrix B. Matrix B will be 10, 8, 9, 6. 9.5e6, 9.56, because it's a decimal. 9.56. Because if you get an error in the machinery unit, you don't really aren't processing signals, you're processing noise, and that's the problem I'm really trying to address. You're processing noise because you don't know you're processing noise, and it's maybe similar to you, trying, but maybe intercepted already, and the game's all over. And that transpose of, so basically the oh, this is really good. Oh, this is really interesting. So the transpose of 10, 8, 9.51 is the 10, 9, 19 over 2, which is an irrational number, but it's basically 19 divided by 2. Let me just calculate that my calculator. So this is 19 divided by 2, and this is like a 9.5. So you do get 9.5, but you get it on the y-axis 1, 1. But x-axis is 1, 1 is 10, and then y-axis 2, 2, 1, 2, 1, 2 is 8, and the y-axis 2, 2 is 1. So basically, you get that transpose once. But 2 transposes are just basically, I love the transpose visual. It just give you because if you angry, you kind of problem. You can get the determinants from the transpose. How do you do that? Let me just get that. We're going to do determinants of this. To be determinant of this, it will be this. So determinants of this would be 66. But basically you get the determinant of what? No. So this one I matrix of 1. So I insert it to A. So basically, I get 10 2, and I get the determinant of this matrix A. So the determinant of it. So this is very good together. So 9 over 2. 8 1 equals minus 66. So you get minus 66, but you get determinant of the matrix, but basically there's no difference, but you get the plus 66. Basically, it shows you have two inputs, but that's what I want to show. I can't remember what I want to show. Basically, this was the thing I forgot to show, but because I forget. But 10 19 2 8 1 is minus 66, and 10 8 this is the same matrix, but just transpose. This is supposed to be the different angles, so you can see you can get so many different variables to this C66 as whether X or Y, but they have to be given modular as a matrix as determined. So this is determinant matrix of this is minus 66 can have two inputs. Minus 66 basically you can see you have two matrices because you can get calculate transpose. Basically, if you have an identity matrix that's 0, determinant is 0, that means there are no transpose, there's no states to it, and that's just the model. If you get something that's non-zero, that is a number, that's the signal, that's what you don't want them to have. The enemy that's have, but literally, my 66 is just good enough for this, because you get 10 x11, 19 divided by 2, x 1 1 2 x22 and then 1 1 8 and that'll be 8 x22 x2 and 1 we get minus 6, but literally because you get minus 6 as the answer to this determinant, but it's just 8, it's just the kind of say of the resolution, because you get structure to, so you get two seeds to everything, so basically you want to go to everything as a dimension of half. Dimension has to be half literally, so you get how you do this is you get 1/8 of it. So 1/8 of this. So let's do this. Let's do this to 1 power of 1/8. So we can do this is just range calculus. We can do to the power of 1/8. What would that be? So let me just say to the power of 1/8. Power to the power of 1/8. And let me just do the calculation. I don't want to count my calculator to break. It doesn't break. I want you to do it properly. So let me just do the definite number 0.8, and obviously 1/8 would be 1 divided by 8. Let's see what the number is. 0.125. This is just the 1/8 or other half polar hour because it's 1/8. It's still fixing up power. Obviously, this one number I wanted, and this would be 1 to the power of 1/8. Sorry. This is like literally annoying me. 8 to the power of k. But I don't want this kind of thing. So basically, let me just try to clear this. Basically, you see a point to this. Okay, this is a point. So this is like a point. Let me just try to. One dot. I don't know. Oh, it can't do this kind of operation. It's annoying me. But listen, it's just annoying because it's like freezing. Let's just do 1/8, 1 divided by 8, because it's not even a half normal rank to the power of 8. So basically, the matrix 1/8 of this kind of system is literally just what's the dialog 1. So you got a diagonal matrix. I love the diagonal matrix. Diagonal matrix is what you can vary with, but it's just rational. It's all sirs, but it's more all measure of noise. That's why I love the diagonal matrix, because it just gives you the same thing, but it's a noise. So we can verify. So you can verify this because it's just noise to the enemy, but it's information to you. But this is the smallest information you can get that can verify. Because it's still information, and that's why I love it. It's dialogue. So basically, from the eigenvector. Basically, it's just signals. That's why basically the sirs are just what defined as what square root of numbers that are that can go to rational reality. Example, this was an example. Basically, an example. For every lambda we do, we have its own vector. Pi, minus pi I, but you get some v, we get homogeneous system. But this was saying. This one's always working. Is dialogue. It's just a signal with the minimum you can get with the maximum noise, and that's why I love the diagonal matrix, because it just verifies, you just see the information and no one knows what you're talking about. You can continue the session. Okay, thank you guys. LSU, I love you, Einstein. Sorry you died. I love you. I'm so sorry. I'm sorry. I'm not sorry, Einstein. I love you. What's your name? Stephen Hawking. I'm very sorry. What happened with you? Why are you in my head though? I love you too. Sorry, man. What happened? I didn't kill you. Leukemia. I won't die with leukemia as well. Leukemia? know what that would look is right. Never die. No, there you go. I love you. So basically, transpose. Who are those people? But you're here now. But I don't know why. I love them, but I don't know why they can't do something. What is important? Anyway, so basically, let's just like I'm looking at Einstein kicking okay on my face, but go to basically I'm trying to go to Trotsky gravitation. Think of it like deep system. Basically, doesn't matter what's altruistic, but if you hear ping and that ping is it's just noisy nonsense that can't be encoded properly, I can intercept, I can get information in my constitution from I'm literally just building things that can save people's life. I don't care whether it happens to sea or not. If we get information someone's dying, we can come to rescue. In Biafra, of course, Biafra, Bight, which I don't care whether it's a sea or not. This is what I'm trying to solve, the NSIGGI protocol. But it's to get the open derivative framework for it too. So get here, what am I saying here? You get ODS. Basically, this is like the framework for verification of calculus, but it's just basically just trace derivatives. Literally, it's just trace derivatives, but yes, trace. The only problem now is tracing noise, having the noise be making sense, and that's the problem. That's the right part of it. Because I'm going to see because there's a noise windows on the ocean, but it makes it hard when you can these noise just appear before you even can talk to them. That's when in the ocean, also in the ocean, you can't really get to it. This is what I'm trying to do. So this is the third derivative, 9c²/2, and get the second derivative, velocity iteration and jerk. Now I don't really like the jerk notation. I like because it's like the jerk. You just go. But jerk is like really annoying. It's like a scalar value, and this is what I'm talking about. The third derivative is what I'm doing because you get the third derivative, 9t² plus 4t plus y, and that's basically the third derivative. The derivative is like association velocity, and then you get the trace. You get the reduction to the trace function. This will be s pi x at 18t plus this is change of the change. This is acceleration, but you get a jerk x triple. S cube, but S just the derivative tracing, and you get 18. But 18 is just a number. This is a scale I'm talking about. This is a scale. This is just a scalar. But this scale can mean so much more if it's handled properly. And that's what I'm saying. The third derivative is like important to me because I like the third derivative because I did forget my problem in my mind because I wrote it down somewhere. We're gonna dig it up. So the third derivative is x to the power of 3 to x to the increase 3. Of time when the time is 18, so every 18 milliseconds you get some information. Every 18 seconds you get some information, and that's where the ping happens. So it seems like television is 0, but this is what I'm talking about. So, for example, you get 18², 18 can be half. So I can list in the halves. I can pole in halves. 18 divided by 2, that will be what 9. 9. So this will be 9 will be a vector. Basically, I'm going to try to do one now. With 9, which kind of 10. So let me just model this simultaneous equation. Let me just do this kind of 10 properly because I don't 9t², 9. So 9t will be 9t, 9. What input is here? 9, 4, 9, 4, 7. 7. This is a 3 by 3 means 7 0, 7 or 1. Because if it's 1 0, no, you can't divide by 0. 9 4 0. But this is a row matrix or requirement. This is a vector. Let me just make it a vector. Let me do a dimension. Let me clean 2 dimensions. 9 4 0. 9 4 wait. 9 4 what? 9 4 7. 9 4 7. 947 and the termination is 18, so I get the half rule. So at the third of it's 18, but 18 is a half of something. So to the power of a half of 18, that'll be 9. 9, because that'll be power of 9 to power of 9. The power of 9. Basically, yes, we equal to the power of 9. Basically, you get to the power of 9. Basically, the best way is just do it to the power of 9. But just basically get everything to 1. But when there's no to the power of 9, the row this will be basically get the crow, basically get the object. Basically, this is like why I love the system. Transpose, determinant, flip. This is 1 1 1. But let's do just 2 dimensions of it. 1 1. So let me just use because I just show you how this works in practice because like I don't want to fuck it up to my projection. So power of 1 9. Basically number of clothes in the first matrix, row in the second. So it's like a 4 7. But this is 4 7. But you can't mix the rows together because you're like it works on the opposite. So to the power of 9. The number of columns get a row. But this is like a literally let's just do 1 1 1. Let's do one. Let's just make it 1 1 1 like a. Let's just make it 1 1. Let's do like a literally just to get the access to the row in a second. So anyway, just let me just put 1 everywhere now because I think I'm not seeing a picture now. Yeah, I love it. So basically, you get 947, which is a row image. Oh, basically, it's the right. Basically, I don't even know do it like this. I just wanna fuck it up. So I don't want to give you traffic. So get the 947. So 947 in row is the row 947. They get this is the same as 111 in them. They get to the power of 9. Just obey. 949 to the power of 9 is 1000. This is just all the noises, but you can use this noise to get information. So basically, 947 111 is just to the power of 9 is it's a half of the system. It's how 9 minutes 9 for every second it's going down, but this is how every second is going 9 millimeters. No. Wait. The time. So every time is going basically every second of a time is going 18, but that's 18 squared. That's 18 divided by 2. That'll be 9, because that'll be the signal 9 units of the signal. That'll be 18. So the 18 will be the other 9. The 8 divided by 2. 18. Let me do 18. Basically, you do 18. Let me do 18. 18 divided by 2 is what? 9. So 9 seconds plus 9 seconds is 18 because 19 because you get it as flip the half. Basically, this will be a half. So this will be a half, not the power of 9. Sorry, Namdi. And that'll be what you're trying to do. So basically, you get the see so basically, so this is half the signal. So every this you're trying to look for. So this is basically information. So you get 947 times b, which is some kind of input that's arbitrary. That's basically scalar too, but someone's listening. So basically, just information. You get, but this information you get. So this matrix here is a third, but it's actually going to be represented as random number. So you can take this matrix as a third. You get two thirds, which are two square roots. So, for example, in the first column, x0 x111 or 000. By computer indexing, you get inside you get the square root of the 338 divided by 8,649 plus 716 plus divided by 9. You get that's the x column, and the y column you get square root of negative square root of 256036 divided by 60543, and then plus 16665 divided by 5. Yes. 4 and get 8. So you get square root of negative 56564 divided. But you get you can compute this correctly, but you look at the answer here because I'm reading out for the systems I'm using. Just do the first three. The first three is only what I need actually. So forget negative squared, you get square root of negative 5864 divided by 60543 plus 3284 divided by 654. Remember, there's two square roots. You have to put the square root sign and the square root, but this just one the noise signal. But the noise signal is just all the information contains all the information and the noise that of that system that you don't know what it is. That's arbitrary because you don't know how the system is configured. That they're using, but basically it's gonna be pi I. So this is just half dimension. They can scale as basically no matter what protocol they use this. If this function represents and the jerk, and this is just a summary equation. Basically what am I doing? How do I do? This is just half the measures. You get a signal. You get a signal you know. But what am I trying to do? We've done everything. For every two vector now. So you're now getting the determinant. So you can now apply the determinant. Basically, let's look at the diagonal matrix. The diagonal matrix will be this. Basically, the diagonal matrix will be like one of the diagonals. Basically, this is actual signal. Because you get noise in the signal, this is actual signal. Yes, this is a signal. Am I right? Yes, this is a signal. Yes. So the signal will be the diagonals. What it should be. If you can compute this, basically you are them. You either them or get information. But you can verify this with the information. That's why it matters because it is the information, but in dialogue. So in XYZ, basically you get XYZ 943 has 3 diagonals, 3 axes you can be at. To get that information, which is where the information is propagates the most. Has a stronger signal, which is what I'm saying. It's 3 axes. You get 1 matrix minus 3 over 5 negative 93 over plus 7 over 2, 93 plus 3 over the square root of 93 plus 7 over 2, and you get that you get the XYZ address, and you get then you get the row B then, because I don't even know, but the diagonal is like a diagonal access. But I don't even know how do you complete this actually? I don't know. I think I forgot it. But the diagonal is like what I do. Because I'm trying to forget, because the dialogue is like a diagonal. It was like basically it's just the signal you're meant to be getting. But you can look at this, it's a signal because the information meant to be getting. But yes, it's just sparse information that your model they get them. So basically it's signal, but it's sparse. But you may not know, you may get the wrong signal. That's what I'm saying. But because it's radio waves, everyone's on a radio wave. Like when you are, that's why it matters. But this is information of the same set. This is all correct information, but it can be incorrect if you have half of it. So this one's all true when you have half of it. So you get 2 that's true. You can't get the full information, but some arbitrary function can apply, and that's what matters. This is just the 2-pointer rule, but it's like 2 pointers in the system because you get half of information. So if you're looking at this first matrix, minus 3 x minus 7 1 2 squared, which is rule x1 x2 1 and 1, that would just be the matrix at the bottom 1. You get that in the xy axis. That's really you're looking at the information as a signal, but you have to get another matrix to resolve that signal, and that's what I'm saying. It doesn't matter if you have one matrix. If you have one matrix that controls everything, that's the same as this like a solid matrix. I think that's the problem I'm trying to admit again, because it doesn't matter what you are doing. Just put yourself to. That's a single program for you. So last matrix, I'm gonna try to do how I'm gonna go. But class matrix is like y1. So you get 3 matrices. You get a triangle. So you get like minus x1 2 minus 5 over 7 x1 3 5 over 7 x2 1 minus square root of 93 over 93 x2 2 41 square root of 93 plus 467 1302, and square root of the 33 plus 33 is 4 times 33 plus 33 square root of 51, and square root of 33 over 33, and they get the opposite thing for conjugate models. And that's what I'm saying. It matters because the same numbers I just said, it's just opposite, and that will be the z axis only. Z axis z x1 z1 z3 y1 x3 z3 y3 z3 and z3. Basically, you get 3 by 3 matrix. And that's what I'm saying. You get what the signal is. Basically, you don't allow noise in the system. Whether it's space or no. But I'm trying to get my one system to get more signal, no noise. Thank you guys.